Dr. Harsh, and thank you to Dr. Tausif and particularly the honorable faculty members of SRM University for inviting me to this talk, which is something I've been focusing on for the past, I would say, 1.5 to 2 years. And going into this particular topic, it also emphasizes on the need of digitization in the sector of wind energy. Typically, now that every process in Industry 4.0 is being linked to artificial intelligence and how we can actually optimize our day-to-day processes and improve our efficiency. So we are very well aware with this AI fact, but how actually we can integrate the concept of digital twin for the condition monitoring of wind turbines, that is something I look forward to discussing here. So as far as the outline of my talk is concerned, we'll be focusing first why we are going forward with renewables, then why wind energy in particular is the ultimate go-to solution, because there are options with solar, biomass, hydropower, but why wind is serving as a very go-to solution, in particularly for Indian landscape. Then, as far as the grid integration is concerned, because obviously we'll be delivering power to the grid, we are we are not focusing on the standalone systems. We are focusing on systems where the power will be delivered to the grid. So in terms of power delivery to the grid, what are the major roadblocks? So what can lead to minor or major failure when it comes to grid integration from wind energy? So basically, we'll be discussing the operation and maintenance roadblocks that can happen when you are discussing the grid integration. Then, in order to overcome these roadblocks, how we can use digital twin. So it's a winning strategy, I would say. People nowadays, especially European companies, they have been focusing on digital twin technology in order to enhance the optimization process. So yeah, we'll see the framework, what actually is present in the digital twin, what is a digital twin first of all, and how we can leverage this concept to improve the overall performance. So first, going forward, why renewables? This has always been a very major question in the power community, why we have to rely on renewables, given the fact that they are intermittent, they are not continuous. But again, looking into the disadvantages, I would say advantages are much, I would say, in favor of us, because obviously the demands are rising, and to cater these rising energy demands, we always look forward for solutions where you can invest less and get more. So I would say initial investment in some of the renewable energy technology is very less, given the fact that you don't have to pay for the fuel price. And that is one of the major attractions, I would say. Investment wise, again, renewable has seen a major interest across the globe. People have been investing in renewables, especially solar in India. If you see, solar and wind, these are two renewable technologies which are neck to neck. I would say investment is quite comparable in both of these sectors. But again, given the advantages, there are also some disadvantages which people are trying to get rid of by using the latest available technology. So again, the main reason why we are going forward with renewables is the fact that your conventional energy, in terms of, let's say, coal, is quite unstable because you are dependent on the supply of coal and it takes a lot of time. Then, if at all, let's say there is some fault in the coal-based power plant, there's a lot of time involved when you want to restart a coal-based power plant. So yes, again, there are a lot of disadvantages and inconvenience, I would say technological inconveniences, which are related to your thermal power plants. So to get rid of them, we are essentially reliant on the wind, typically renewables, I would say. And again, yes, there is an added advantage of the green energy that is being produced as we use renewable energy. So yes, that's one added advantage. Now, this particular slide is very important as far as the electrical engineering is concerned. As far as the power engineering is concerned, there's always an imbalance between generation and demand. As you can see from this particular seesaw, that there are instances where either of the two, generation and demand, they are not equal to each other, right? There is a lot of instances where you are generating more than what you require, and sometimes the load becomes excessively large. So in that case, what happens is you are again reliant on additional sources of power. So this again, the generation demand seesaw, why we are focusing on generation demand seesaw is that your condition monitoring is because of this, the need for condition monitoring, especially in power sector. The need for condition monitoring arises from this generation demand seesaw. And why the big generating companies, they are in trouble is because the demand keeps on rising, the demand for energy that keeps on rising. So it's a monotonic, I would say, function. Mathematically, if you want to describe the demand, it would be a monotonic function. It keeps on increasing with time. So what happens is you cannot actually manage the demand side. So it becomes tricky. You cannot tell people to, shut down your load. You cannot tell industries to use power only in a specific amount of time. That is quite tricky. So entire burden of this, of handling generation demand seesaw, it it is a burden on the generation companies because they need to regulate their generations. And usually this is what is the scenario, especially in India, where the demand is, it keeps on rising and suddenly it falls. So it's a big headache, especially for the generation company. So what they do, essentially, they are using forecast algorithms. I would say they need to forecast certain parameters, essentially the parameters which can help them to balance this generation and demand. So if you have an accurate forecast, if your forecasts are reliable, then I think it becomes quite easy for the generation side company or the gencos to balance between the generation and demand. So again, what we do, especially in renewables, because the topic is regarding wind energy, your forecasts are essentially related to weather parameters. So we are looking at the parameters such as wind power, solar power, irradiation. Then again, you sometimes forecast the, in terms of hydropower. If you are looking for forecasting, then you'll forecast the runoff. So again, parameter wise, if you see, forecasting can be very critical, and the results from this forecasting will directly impact your generation and demand. So statistically speaking, renewable has seen a lot of growth in, I would say, past 2 decades. People have been investing, especially in India. If you see, solar is one of the renewable sources which is being promoted at an, I would say, impetus rate, right? The promotion wise, solar is being promoted at a larger rate compared to wind. Obviously, the investment cost, one of the reasons what I feel is the lot of investment cost is involved in wind turbines, and the readiness of people, because you need a lot of area land wise. These resources need a lot of installation area, so it becomes quite difficult again, politically. And agriculture, for example, if there's an agricultural land and you wish to set up a wind or solar park there, so it becomes quite difficult, monetary wise, and then policy framework becomes quite difficult. But again, people have been accepting this fact that the advantages are more significant rather than the disadvantages. So if you see, statistically, 40 gigawatt of installation is there in India for wind, and entire 40 gigawatt is onshore. Now, this is something really important and interesting, that the all the wind parks in India, if you see, they are all onshore. They are not. So we do not have a single offshore wind farm. Reason being, the policy framework. Again, people have been investing a lot of their time in policy framework, but again, in terms of action, we are quite late. And because taking advantage from our well-defined coastline, I would say offshore wind farm would attract a lot of investor and would solve a lot of existing grid problems that we have. In fact, we can also go ahead with the isolated wind parks, if we are looking forward to, let's say, powering an island, or let's say if you want to even transport energy to a neighboring country. So a country which again would be operating on same frequency level, let's say 50 hertz, or even if they are operating at 60 hertz, this asynchronous operation is also feasible. So one place where I would I think is India would be looking forward is investing in offshore wind energy. That is something I would say is something to look forward to. Now, this is again a chart where how the distribution is concerned. If you look at solar photovoltaic is 28%, then you have solid biofuels. Going ahead, you have wind energy again. So there's neck to neck competition between solar photovoltaic and onshore wind energy. Offshore, we do not have any, so there's no percentage dedicated to offshore wind energy. Hydropower is again one of the major attractions of Indian power portfolio, I would say. We have a lot of dams. Again, the river flow in India is quite brilliant due to the Bay of Bengal. Then you have your Arabian Sea, and then you have Indian Ocean. So consistently, India has been receiving a good rainfall also. On an average, if you see, so runoff, water runoff is quite decent. So that's the reason why you see the 33.1% of the generating of the installed capacity share that you have is dedicated to renewable. But again, this block, the brown block represented by onshore wind, this is something which is likely to increase, and we would see a new block in future which would be dedicated especially to offshore wind energy. So yeah, that's this just a renewable landscape of how people and investors they are concerned with their money as far as energy is concerned. Now, if we are focusing on wind energy, to be very specific, what are the pros and cons related to wind? So one major pro is that you have a lot of resource available. In terms of resource, the resource is available in abundance, and it's free of cost. You don't pay anything. You don't pay to use wind. It is available for free. It is a natural process. And as a result of this, the push in the green power portfolio in India also, if you see, since last 5 to 10 years, the push in the green power portfolio is something to look forward to. People are coming forward. In fact, if we notice, Adani is one of the major player who has been investing significantly in solar and wind. So again, for the next, I would say, 10 to 30 years, you'll see a lot of green power portfolio. And again, employability wise, it's a big pro. People have been getting a lot of jobs, so there is job security. You need skilled labor. Again, as far as wind and solar are concerned, especially installation part and maintenance part and operational aspect, you need a lot of skilled labor. And India is rich in skilled labor. The employability wise, you would say wind is something to look forward to. So now when it comes to wind farm, what do you need essentially to run a wind farm? You need a wind turbine. The turbine looks something like this. As you can see, this is a rough layout. And if you look at this picture, you'll find that there is a turbine which has blades. It is there are multiple turbines. Again, it's a good landscape. You get a lot of wind available here. Again, one major requirement to establish a wind farm would be that you need a good resource. So you won't typically install a wind farm where you do not receive wind. So what happens is when people are going to invest in a particular wind farm, they are going to look forward to a place which receives wind speed. So you need a resource assessment to be done. So assessment is done on the typically on a wind farm area where you would be analyzing what is the wind speed, average wind speed, what is the wind direction. And you do not do this for 1 or 2 days. This is something which you do for years. So typically 5 to 7.5 years is the time which is being spent on the resource analysis. Only then you can take a decision. Otherwise, if you take a decision 1 to 2 days, or even if let's say you take 6 months or 1 years of time, the climate can change suddenly. And as a matter of fact, you won't be investing in a place which does not give you substantial returns. So ROI is again a major criteria for the investors to look forward to. And typically, if you observe a turbine, what you need inside a turbine is you have your rotor blades, which is obviously essential. You need enough wind thrust so that these blades can rotate. And then you have your gearbox, which is responsible for amplifying your speed. You have a generator. Now, again, generator topology is something which has seen enormous growth over last 20 years of time. You have a lot of different types of generators which are installed in wind turbine. Starting with the squirrel cage, you have induction generator, then you have doubly fed generator. Now people are focusing on permanent magnet synchronous generator. So again, the magnetism of that magnetic field is constant, and then you don't need a gearbox. So there are driveless turbines also. You don't need a drivetrain. It is essentially direct. The rotor is connected to the generator. So yeah, topology wise, there are a lot of different topologies of turbines are there. Then you need a soft starter, because essentially when the turbine starts, right, it would behave as a motor, because a generator and motor operation, they are dependent on typically slip speed. If you're using a if you're using an induction generator on an induction machine, essentially the slip would decide your operation in terms of motoring or generating. So initially the machine behaves as a motor, and then gradually when the thrust of wind, when the torque received from the incoming wind speed is high enough, then it starts generating. So again, when you're generating, you need to limit current also, because you do not want to damage your generator. Generators are very costly machines. They have armature windings which carry a certain amount of current, and you would not want your generator to get damaged quite often. So again, you need to take a look at your generator also. You need to look at the health status of your generator. And essentially, what binds this entire thing is a good data acquisition system. Now, data acquisition system or an instrumentation system in general also we find very relevant to electrical and control engineering, because until and unless you do not have a sophisticated instrumentation system, you won't be able to monitor your critical assets, right? So again, the crux of this particular presentation would be focused towards a sophisticated instrumentation system, because as far as the condition monitoring is concerned, or if I want to monitor a particular turbine, or even if component of a turbine, I would be reliant on data part. And as far as data is reliable, it can be only treated reliable if you have a good instrumentation system. So yes, you also are looking forward to an instrumentation system where you can get multiple data. High frequency data is sometimes desirable because you are looking at a gearbox operation which is continuously under stress from the incoming wind speed, and then there is a coupling involved. So yes, that's what you need to run a wind farm. A good turbine, again, inside the turbine you need couple of sophisticated instruments, you have critical components, and more importantly, these days, there is a lot of threat of cyber attacks on your grid tied wind farm. So if, let's say, if you have a cyber attack on your wind farm, the entire parameter and the operation of wind farm can be altered. So this is something which has now gained significant importance from the R&D team across the globe, that how to prevent your wind farms or essentially individual turbines from cyber attacks. So you need a resilient system, a system which is not only delivering power to the grid, but also is self-sufficient in terms of detecting what are the possible threats to your wind turbines. So this, yes, the layout, how does the layout look like for a wind turbine? As you can see, layout of a farm, and you have multiple turbines. Each turbine is located at a certain distance from the other turbine, known as the longitudinal and lateral distance. So you need to maintain, again, a significant distance between the two turbines. Otherwise, there will be a lot of crosswind involved. And because of this crosswind, what happens is that, as you can see, the turbines which are placed behind the front row turbines, they usually experience less wind speed. Now, the principle of wind turbine operation states that larger your wind speed, right, more is the power generated. So there's a cubic relationship between power generated from a wind turbine to the incoming wind speed. So if your turbine is receiving less wind power, if your turbine is receiving less wind speed, you will generate less wind power. And there's no point of a turbine operation which generates power which is far less beyond its capability. So installed capacity is something which a farm operator always looks up to. My objective is always to operate near the optimal point where I can maximize the power generation. So that is also one of the objectives of your turbine operation. Now, what are the critical components of your turbine? As you can, if we look at inside my turbine, you have something known as the two. So if you want to categorize, there are rotating components, and then there is a non-rotating equipment. Rotating component can be classified like you have gearbox, you have generator, and you have your rotor blades. Non-rotating would be a nacelle, essentially the box that you see in this particular slide, the box which carries your generator and gearbox. So that is non-rotating. Again, obviously, you have your tower. Now, tower is also one of the important components because your wind turbine tower always faces significant vibrations and oscillations because of incoming speed. And because of this vibration, what happens is the structural integrity of your tower, it weakens over a period of time. You'll find that the foundation of the turbine is no longer strong that it was at the time of installation. So this is also a, one of one of the, I would say, core research areas in wind turbine community, how to minimize the oscillations or vibrations of the tower. Because if tower is not strong, then it cannot hold your nacelle, and essentially the heavier equipments which are inside your nacelle, they would suffer from malfunction. So yes, tower is again very important part. Gearbox is something which is, I would say, the heart of wind turbine, where your entire turbine operation is reliant on how good your gearbox is performing. And essentially, because your gearbox is connected to the rotor, whatever is the rotational speed of your rotor is directly impacted on your gearbox. So if your wind speed fluctuation is very high, I would say that the first and foremost equipment that is likely to get damaged or get likely to malfunction is your gearbox. And because of this uh, fluctuation in wind speed, the critical aspect of condition monitoring is the gearbox itself. So now just let us look at the inside of nacelle, what it looks like. You have essentially a rotor hub that binds all the rotor blades, and then you have a main bearing. Main bearing is connected to the gearbox via main shaft. So this is the main shaft where majority of vibrations, they are transmitted via this shaft to the gearbox. And then this gearbox is connected to your generator. Your generator is the generator topology, as we discussed earlier, could be your squirrel cage generator, or you can have a synchronous permanent magnet synchronous generator as well. And then you have high speed coupling because you are amplifying your speed. So there is low speed shaft and there is high speed shaft. So usually the area of interest in research community, if you are doing condition monitoring, is the high speed shaft and the high speed bearing. So there are two important components right after the gearbox. What you have is a high speed shaft because the generator is rotating at a speed of 1800 to 2000 rpm, whereas your gearbox is whereas your rotor is operating at a very low speed. I would say maximum speed that rotor can go is 60 rpm. So from 60 rpm to 2000 rpm, your gearbox is amplifying basically. And where the majority of the damage happens is the gearbox part only. Inside the gearbox, now you have gears. You have a multitude of gears. The gears can suffer from wear and tear. There can be abrasion. Then there's a lubricant present inside the gearbox, because obviously the temperature can go to a very high value. Inside the gearbox, the temperature can go as high as 70 to 75, sometimes 80 degrees Celsius. So to cool down your gearbox assembly, you need a lubricant. And sometimes lubricants also suffer from contamination. So that is one major problem in our gearbox as well. So now going forward, why once we have looked into what is the what are the components of wind turbine, where I need to focus. We are now slowly shifting towards the idea of condition monitoring. Is it really required in wind turbine? Do I go forward with this particular framework? If I go forward with this framework, then where do I need to focus? Because the turbine has a lot of rotating and non-rotating equipments. So where would your focus would essentially lie? That is something that we need to look forward. So if you look at the uh, meaning of condition monitoring, what Wikipedia says that is, it's a process, right? It's a process. You not do this one time, you do it continuously, and you do it for a machinery, essentially a machinery which is under operation, which is doing some useful work, and you try to monitor a parameter of this machinery. Now, parameter of machinery could be vibration, it could be temperature, it could be acoustic noise, and it could be it could be, let's say, pressure, it could be humidity, etc. Now, when you measure these parameters, what you are ultimately trying to do is you're trying to monitor a change, right? Whether these parameters, do they change? If they change, how significantly they are changing? And usually the changes in these parameters, they are sometimes indicative of a fault. So if a fault is to be developed inside your wind turbine, what type of parameter you will measure? Because if you measure the right parameter, then you can accurately diagnose whether the fault is present in your machinery or not. Otherwise, if you are measuring the wrong parameter, you'll never come to know what is wrong with your machine. So essentially, it's a process, right? Condition monitoring is a process where you monitor a parameter, and the result of this condition monitoring process, is majorly a decision that you take, right? Because you are worried about the health of your equipment, because you do not want to replace your equipment again and again. It is very costly affair. So essentially, if we are going forward with this condition monitoring approach, you'll be looking, all that you'll be looking for is would be a change. And these days, the modern day term is also predictive maintenance. So predictive maintenance, condition monitoring, these are, I would say, synonyms. Majorly, predictive maintenance is a part of condition monitoring. And to deploy these condition monitoring systems inside your wind turbine these days, a lot of AI techniques are always used. So the perspective again would be to monitor the health of your sensitive equipment, and what type of equipments that you see in power system. They could be compressors, it could be pumps, electric motors, in the internal combustion engines, and essentially the turbines. So all the rotating equipment, industry 4.0, these are the equipments which suffer from potential damage. And because this is a very heavy machinery, this is a very costly machinery, you would like to have a condition monitoring framework for these rotating equipments. So essentially, your idea is to monitor a particular parameter, and once you monitor this particular parameter, you should be in a position to take a decision whether to take out your equipment for maintenance and repair, or to continue the operation. So what are some common condition monitoring techniques in industry 4.0? You have vibration analysis, very common popular technique. People in industry 4.0, especially with all the rotating machines, vibration analysis is one of the methods which is, I would say, 90% of the time they would be reliant on the results obtained from vibration analysis. Then you have ultrasound techniques, you have infrared thermography, then you have oil analysis, and then you have acoustic emissions as well. Now, in terms of infrared thermography, you are essentially reliant on image-based analysis. A part of computer vision is always involved. You take infrared images for the particular equipment, or maybe you can always do infrared thermography on one part of your equipment. Let's say you are focusing on one bearing of your machine. If that main bearing, if it is, so whether the bearing is leading to a particular fault or not, that decision can be taken based on the results from the infrared thermography. Oil analysis is something which is done in transformers quite frequently these days now. Transformer, if you see, it's an electrical machine which transforms a particular input level voltage to another input output level voltage. But what holds that entire transformer operation is presence of an insulation. Oil is again a very good insulator for the transformer. Now, the degradation of oil, if I were to talk about condition monitoring of a transformer, 99% of the time I would talk about oil analysis, because how your oil degrades over a period of time indicates the quality of your insulation. And when to replace that insulation is again very important. You cannot replace it before time, because otherwise what you're trying to do, you are investing unwanted cost in O&M procedures. So yes, it has to be intelligent, right? And that's why there are a lot of different techniques in condition monitoring that are involved. Previously, what people used to do, they used to do time-based maintenance, TBM. As you can see, time-based maintenance is a maintenance procedure where you decide at a fixed interval, you'll be taking out your machine for inspection. So, for example, I can fix a time, let's say 6 months from today, I'll be taking out my machine, or let's say 4 months from today, I'll be taking out my machine. Now, major disadvantage of this particular procedure is that you are actually trying to take out your machine. For example, if I can share this particular slide from this slide, machine health versus time. If the failure is bound to happen somewhere here, and you take out your machine quite just before the failure happens, so then you do not have enough time to take your decision, right? So this is reactive based maintenance. You react at the time of failure. This is one type of maintenance. So reactive maintenance is it could be treated as an example of time based maintenance. So there could be unnecessary shutdown in your factory, right? You have taken out your machine. Let's say it is a wind turbine. So if you are going with time based maintenance, you take out your wind turbine well ahead in time. So your turbine is still in position to generate energy. Your turbine is still in position to contribute power to the grid, but because of your fixed schedule, you have decided to take out your turbine. So as a result, what happens? Your generation falls down, your installed capacity goes down. And because, especially in power systems, if I were to speak with proper power system topology and terminology, the capacity factor would go down essentially for a wind farm. Wind farm has a lot of turbines. Each turbine contributes to capacity factor. So if you are in a position to generate 10 gigawatt, but then you have taken out your turbine just because you feel that there could be a fault, your capacity goes down, and essentially then you are not generating enough power, and hence the revenue would be impacted significantly. So this is a major disadvantage, I would say, for time-based maintenance. So what could be several examples? Let's say tuning up the furnace every year before winter. You could change the properties of furnace. You can clean a furnace, right? Cleaning debris out of gutter every 6 months. Yes, so that is something that we see on day-to-day basis in our locality and neighborhoods. Visually inspecting fire extinguishers each month. So yes, if you have fire extinguishers installed in your factory or plant, you can have a visual inspection. Changing an air filter of compressor every quarter. Again, yes, people do this quite often, because sometimes these places are inaccessible. So one would go every now and then. So what they do, they try to fix a particular time frame to take out these filters, and then they install new filters. lubricating pumps every 6 weeks. So you may change the oil for the pump, lubrication oil for the pump, even if the oil is in good condition, but still you would do because you have fixed a time frame. So essentially, these are common examples of what could be time-based maintenance. As an alternative to this time-based maintenance, we have a preventive maintenance. So what you do is you take a prevention. You measure the condition of your machine in terms of some parameter, whether your machine is healthy or not. You measure in terms of some quantifiable parameter, and then you take out your machine for repair. And then based on your action, the machine health improves. So as you can see in the second graph for the preventive maintenance, you have taken a decision to take out your machine here, where there is a mechanical symbol of gear, and then your condition improves. So once your condition improves, you can still use it for a larger amount of time. If you would have continued to use your machine would have failed at this time where the cross is marked, right? So, but you have taken some decision and then it continues to run for a longer time. So this is one example of preventive maintenance. Again, you have a technique which nowadays people have been focusing more on is predictive maintenance, where you predict when the fault would happen in future. And because you are trying to predict a trend, you are likely to make an error. That's a straightforward, I would say, fact from this type of predictive maintenance, that you are taking a decision about future based on your current information. So whatever is the current health of your machine, based on that information, you are likely to project a trend. Whether that trend goes upward or downward is dependent on the current state of your machine. So you come to know in advance when your machine is going to fail. Previous two techniques, what we have discussed here, reactive and preventive, you take out your machine without knowing the fact whether it is still usable or not. So that always is going to lead to errors in terms of uh, you're not guessing, you're just making a guess, right? But again, in terms of predictive maintenance, you're still making reliable guess because it is based on the current data always. We do not inspect current data in reactive and preventive maintenance. It is just a time-based maintenance. So you are taking a decision strictly based on some random time frame. And whether that time frame can actually be useful to you or not will only depend on the current health of the machine. So yes, predictive maintenance is something which people follow a lot these days, especially in industry. And what is the main advantage of this predictive maintenance, also known as condition-based maintenance, is that your maintenance costs reduce. Over a period of time, you'll find that your O&M cost, which is a major cost in any industry, O&M cost is a major cost. That will significantly reduce if we go with predictive maintenance. Your downtime, again, very important criteria. Downtime is a time associated when your machine is not working. And when your machine is not working, it is essentially not contributing to any, I would say, productive work that your industry or your plant is intended to do. In terms of wind farm, you take out your turbine, one turbine goes out of operation, it is not contributing to the grid power. So what happens? The grid is receiving less power than what it is expecting to receive. Extended asset life, yes, the lifetime of your equipment gets increased significantly because you are predicting well ahead in time what could be a trend. And based on this predictability, usually people take correct decisions. Decisions are known to them. They know what is the decision to be taken once a particular trend is known far ahead in time. So this decision, it essentially leads to increase in the asset life. Cost savings on prematurely changed resources, yes. So because O&M procedures are very costly, if you do a procedure based on time maintenance, you would be investing a lot of money even if the machine is still in position to run. So unnecessary cost expenditure is happening because of a certain predefined time frame that you have decided. So to get rid of that, one can go obviously with predictive maintenance, where your costs can be significantly improved on your O&M part. Now, coming back to our wind turbine, essentially we have just discussed the preliminaries for condition monitoring and predictive maintenance. Coming back to wind turbine, why wind turbine condition monitoring is important, and if you are going ahead with the turbine condition monitoring, what would be the major objectives? One is obviously to maximize energy production. You are always looking forward to the scenarios where the delivery to the grid, power delivery to the grid, is always on the higher end. Like, you do not want to generate less. Obviously, there is a revenue involved for the generator companies as well. You're looking forward to minimize your downtime and repair cost. Yes, again, a very major, I would say, objective of turbine condition monitoring is to minimize downtime, extended equipment life, and improve safety. Safety and reliability of your turbine is something that governs the entire operation. If your turbine is, let's say, it is susceptible to failures and incipient faults, then the grid becomes unreliable. So people won't be relying on a certain resource of energy if it is not safe and reliable. So condition monitoring also aims to improve the safety of your turbine overall. Now, going forward, if I want to design a framework for my wind turbine condition monitoring, what would I focus on, right? Because we have discussed that in the beginning of our discussion, that we want to digitize. It's a digital twin, right? So digitization essentially involves gathering significant amount of data, and this data driven framework is the highlight of this industry 4.0, I would say. Entire industry 4.0 framework, if we want to talk about it, is, I would say, one of the major aspect of that framework would be how we can digitize our assets. And why we want to digitize our assets is because we want to improve their reliability. We want to extend their life. We want to optimize them. We want to save our costs. So for wind turbine, how would a framework look like? So if you see, you have a turbine which is generating power, and then you have a database. You have a SCADA database. So SCADA stands for supervisory control and data acquisition. So your operational aspect of wind turbine, if you want to monitor, we usually collect SCADA data. Not only we collect SCADA data, but we also collect several different types of data from turbine. One of the major, I would say, important data from turbine would be vibration data, as you can see here in this particular log diagram. The blue graph, the first graph that you see, this stands for the vibration data. So very high frequency vibration data is collected from the turbine bearings. You can collect the same from generator, and again, bearings, you have high speed bearing, you have low speed bearing, and the vibration data from these two bearings is essentially collected. Then you have time series data. Now, time series data is essentially the operational SCADA data. You can monitor the temperature of the bearing. You can monitor the what is the voltage of the generator output, what is the current, then what is the temperature of the nacelle, essentially the box where you are keeping your gearbox and generator. What is the temperature of the oil inside the gearbox? Oil is used as a lubricant. So if there is a contamination in your lubricant, you will be monitoring the temperature of that oil. So how that temperature varies over the period of time, it could be an indicator of a potential fault in your gearbox. Then you also measure noise, acoustic emissions from your turbine. Sometimes people can diagnose whether a fault is present or not just by listening to the type of noise that your machine makes. That is quite easy. That is quite an efficient and easy technique to diagnose what type of fault it is. Now, once you collect all these datas, this data becomes a multimodal data. Multimodal data is essentially the data which you gather from different sources of your data. So vibration is a different source, operational SCADA is a different source of data, and your acoustic emissions is a different source of data. So essentially these modalities, if you combine them and you feed it to your machine learning or deep learning framework, you can get some meaningful information, whether a fault is present or not. If a fault is present, then what type of fault it is, right? And why the fault is present, what are the major reasons behind that particular fault. So fault diagnosis is a major aspect of, I would say, condition monitoring. So if you are doing condition monitoring of your turbine, one aspect would be essentially to monitor what type of fault is developed in the turbine and what are the reasons behind the presence of that fault. So yes, this is the sensor configuration inside the turbines, because we have also discussed that the instrumentation and sensorization of your turbine is a major, it plays a major role in condition monitoring. If you want a good condition monitoring framework, you are always looking forward to an instrumentation system which can be reliable and which can be as precise as possible. So precision and reliability are the two, I would say, characteristics of a good instrumentation system. So as you can see, there are a lot of sensors. There's an accelerometer which measures the vibration. Vibration is measured in different stages. You have low speed bearing, you have high speed bearing, then you have the vibrations on the bearing shaft, then you have on the bearing gearbox bearing as well. Then you can measure process values like ambient temperature surrounding the generator and gearbox. It can impact your faults. Then you have parameters like power generated. So if there is a lot of variation in wind power generated, it could show whether an anomaly is present or not. Then temperatures, in particularly, we are measuring gearbox bearing temperature, what the temperature of the main bearing. Main bearing is, as you can see, it is present here on the low speed shaft of the gearbox, as it is connected directly to your the rotor hub. Rotor hub is essentially the part which consists of the blades. And if your main bearing is working well, then you can say your gearbox operation is good. And essentially, it is all dependent on the main bearing. So if main bearing fails, then you won't be in a position to amplify your speed, because it's all connected, right? And the entire gearbox operation would fail if the main bearing fails. So essentially, the speed of the shaft and the main bearing, again coupled with the temperature and the vibration readings, so this reason becomes quite critical for the entire turbine operation. So this is something where a lot of researchers have individually focused. Overall, you can focus on the generator aspect as well. You can focus on the high speed bearing, you can individually focus on the gearbox, but collectively, if you want your results to be optimal and trustworthy, you will be focusing on the main bearing of the turbine. So yes, this is how the faults look inside the turbine gearbox. You have your bearing cracks, right? The cracks develop over a period of time. There could be a fracture, as you can see. So there could be a tear between the two tooths of the gearbox. And again, you can see there's a lubricant. There could be contamination in the lubricant of the gearbox. This could lead to malfunction. Again, if you look at bearing itself, bearing has several kinds of faults, starting with the inner race fault. So on the inner race of the bearing, you can have one fault. On the outer race of the bearing, you can have one fault. And then you can have faults or cracks on the ball bearings, right? Or on the, so there could be a roller defect, that what we commonly categorize in industry. So yes, these are certain faults which are there in a common rotating machinery, and typically it would be present in the turbine gearbox as well. So now to overcome this, the main highlight of our talk is a digital twin. Why digital twin we want to use first of all, and what is a digital twin, right? And how this twin can be useful in diagnosing fault. So if I were to define Traditionally, a digital twin, it's a virtual representation of your physical asset. So any physical asset, if you have, for example, your gearbox, how you can transform or how you can create a virtual replica of that gearbox. Virtual replica would essentially mean that you are trying to represent a physical asset in form of mathematical equations, right? And those mathematical equations essentially would determine the state of your physical asset. So if I say, for example, that y is equal to x square is an equation, right? Where x is my input and y is my output. So the output of an asset, if I can represent by y, and if that output is governed by some input x, so essentially y is equal to x square would give me a functional mapping, right? If I can input some value of x, I can get corresponding values of y, right? And based on the values of y, I can take a decision whether my equipment is working fine or not. So if y goes beyond some threshold, if there are very large values of y, which usually you would not observe, then you would be in a position to understand that yes, something is wrong with your physical asset. So digital twin essentially, it's a virtual representation of any object, right? And that virtual representation is always trying to give you some meaningful results. One meaningful result could be whether your equipment is healthy or not. So it can give you a binary status in terms of 0 and 1. 1 would mean that yes, equipment is working okay. 0 would mean yeah, that something is wrong with the equipment. So the essential objective of digital twin would be to create a virtual representation in form of mathematical equations. You can use machine learning or deep learning approach to give you some quantifiable output which you can use to make a decision. We are discussing this essentially because we want to improve the decision making capability concerning the wind turbine, and one way is to go ahead with digital twin. So what are the examples of digital twin? You can have a digital twin of a car, of a building, of a bridge, or of a jet engine. This virtual representation can give you certain idea about life cycle, whether your component or asset is going to fail in future or not. So every digital twin has certain objectives which it needs to fulfill, right? And to create a good digital twin or a reliable digital twin, you need to collect data from your physical asset, right? So data collection from your asset, again, it is fed to this virtual model, because virtual model cannot work on its own. You need to give some predefined data, like how in machine learning there's training data involved. If you want to create a prediction model for any particular variable, you need historical data. Based on the historical data, your machine learning algorithm will try to understand what is the pattern inside that data, whether the data is monotonically increasing with your input or whether it is decreasing with your input. So based on that data only, we can function. So a key aspect of digital twin would be how well you collect your data. And not only you have to collect data, you also have to collect relevant data. I can collect thousands of variables, but what if those 1,000 variables are completely useless, right? Then in that case, I cannot make an efficient digital twin. To create a digital twin, you need data which is actually useful to you, which can give you some meaningful insights about a particular process. So if I want to make digital twin for a cup, which is a cup of tea, right? So digital twin for a cup of tea, no one has thought till date, right? If you ask anyone, it would say the guy has gone crazy. How you can make a digital twin for a cup of tea? But in reality, it is possible, right? You can come up with equations that can actually show that how quickly the temperature of tea falls down with time, right? If you can come up with equation, then that's a digital twin. That's exactly what you're looking for. So a cup of tea, right? If you keep it on table and let it cool, right? So that is a physical process that is happening. If you can describe that physical process with some mathematical equations, then this is known as a digital twin. Same thing we want to do, but now our object is wind turbine. So in wind turbine, I need to look at what are the critical sources of data from where I can gather meaningful information. So significance, yes, why to go for ahead with digital twin? You want to diagnose fault, you want to predict the lifetime of your equipment. You can actually predict when your equipment is going to fail in terms of number of days or weeks, right? So time to failure when your equipment is likely to fail. Optimizing model design and operation, yes. So if you can optimize the model design in terms of dimension wise, if you can, let's say, change the dimensions of your product, then maybe you'll be saving a lot of cost and space. And against that improvised cost and space, you are expecting a much better operation. So efficiency, you would like to increase parallelly. Then in terms of energy sector, you would like a reduction in levelized cost of energy. So this is something which has always been a critical area for researchers, how to minimize LCOE, right? Levelized cost of energy, because this is something that directly impacts the operational revenue of your particular plant. So yes, this is an example, just a rough framework of what digital twin looks like. You have your physical asset. Let's say this is an airplane. So airplane is my physical asset, the asset whose digital twin I want to create. So this layer is known as physical space, from where your physical asset is present. Via this physical space, you collect data via sensors and you store it in a database, right? So sensors are used to collect data from this physical asset, and they store that data and it is stored in a database. Now this database becomes a central aspect for creating a digital twin. And a replica of this physical space is a virtual space. So I would say, if you can see in this particular virtual space, this airplane is a virtual replica of your actual airplane, right? And this can only function well if you collect data from sensors. So continuous data monitoring from your physical space via sensors is essential for working of virtual space. So virtual space and a physical space, these are two, I would say, key components of digital twin. Whatever actual physical device you have, a equivalent virtual model has to be developed, and that can be only developed if you are collecting continuous data via sensors. Again, whether that data is good or not, whether the data is meaningful, whether you want to reject certain part of the data, for that you need user input. So human intervention, again, you can see here, user input. User input stands for your human intervention. So humans have to intervene, right, to see whether the database collected is actually meaningful or not. And together with this physical space and virtual space, you create a digital twin. Outcome of the digital twin could be diagnostics, forecasting, visualization. You can see trends in your data, right? And these are basically simulations generated by your virtual space. This simulation can tell you actually what is wrong with your physical asset, which is airplane in this particular slide. So if you want to take a corrective action with your airplane, let's say you want to replace the current engine of your airplane, so that decision can be only taken if you know what is the forecast value of the pressure in future, or what is the remaining useful life for that particular engine. If that life is coming to an end, you would essentially take a decision to replace the current engine and uh, uh, fit it with a new one. So yes, that type of critical decisions need to be taken, and they are taken together with your data collected from the sensors, from the physical layer. So yes, that's a quick infographic of digital twin, right? Now there are various types of twins involved. As you can see, process twin, product twin. Process twin is for a particular process of your power plant or operational aspect. Product twin is a digital twin essentially dedicated for a particular product, right? Then you have a system twin. System twin is a broad level twin. I would say if you consider entire system of assembly, you can make a digital twin of that. Then you have a performance twin. Performance twin essentially is used when you are concerned about performance of a particular plant or performance of a particular part of an assembly. So to optimize that, you can use performance twin. Then you have maintenance twin. Yes, this is something which we are discussing. So digital twins for condition monitoring is essentially a maintenance twin, because you are taking decisions which are based for maintenance, right? Whether to go for maintenance or not. And if we are going ahead with the maintenance, when you are going ahead, what is the right time to conduct the maintenance procedure. So the twin associated with the maintenance is your maintenance twin. And similarly, there is supply chain twin as well. Essentially, this is used for inventory purposes in your infrastructural and e-commerce. Especially, people are using a lot of digital twins for e-commerce and uh, your I would say process industries, right? If your supply is critically important, so to forecast your supply chain procedures, we can use supply chain twin. For wind turbine, again, the purpose would be to diagnose faults in blades, gearbox, and generators. These are the three rotating equipments as we have discussed earlier. For a wind turbine, blade, gearbox, and generator are the critical, I would say, rotating places where one can essentially expect fault. Then you have early fault detection. Not only you want to detect fault, but you want to detect it way ahead in time. And once you do that, then you are in a much better place to conduct operation and procedure. Then you are looking forward for immaculate sensorization, because as we have seen in this slide, that this digital twin cannot work well if you do not have immaculate sensors. So immaculate sensors, I would say, these sensors have to be essentially reliable. The data captured from these sensors should reflect the true data, right? It should not reflect false data. So if that happens, then you cannot take a good decision. Delay-free communication between for physical and virtual space. So as you can see from this particular slide, the transfer or communication of data via sensors, again, this has to be wirelessly transferred. Whatever data you collect from the sensors, it needs to be transferred to the your virtual model where you have deployed your machine learning algorithm. So this has to be delay free. You cannot expect a lot of delay between transfer of data from the physical space to your virtual space. So that is one of the objective. For wind turbine, you can see, yes, this is what a framework would essentially look like, wherein you have your turbine. So turbine is your physical layer. So this physical twin is your actual turbine in your wind farm. You have sensors, you have actuators. These sensors, they transmit data. There's a communication happening between the physical layer and digital layer. The data is transmitted, and then based on the data collected, you use a machine learning or physics based machine learning model to draw some kind of inferences, right? What could be these inferences? That there could be some alarms, there could be diagnosis of faults. You can do prognosis as well. Prognosis is something related to the remaining useful life of your critical components, whether this gearbox is reliable or not. If you want to conduct a test on that, then you would carry prognosis process, and the result of prognosis would be how many days are left for your gearbox to fail. So it is a what if analysis. What if this happens? What if you take this corrective step? What if the turbine lifetime improves? So that kind of decisions that can be taken from this digital twin. You can also model uncertainty concerning a particular turbine equipment, whether a particular equipment is reliable or not, how the uncertainty of parameter impacts the performance of a particular equipment that can be measured, and the output or the inferences from this digital twin could be that you can improve design. Let's say you collected some data and you found that there could be a change in the design parameter of your gearbox, right? If you can, let's say, change the gear ratio, then probably your gearbox would run for a longer period of time. Or let's say if you choose some accurate sensors right? Suppose if you are working with some initial set of sensors and then you feel that you need some more sensors to collect more efficient or reliable data, then that could be one of the inference from the digital twin as well. Now, this is a more detailed and I would say a technical block diagram for the wind turbine digital twin. As you can see, starting with physical layer. So there are three layers essentially. If you can see here, there's a physical layer, there's a digital layer, or also known as virtual space. So what virtual space we have discussed here, right? This is your physical space. This is your virtual space, also known as digital space. So these spaces, they are separated by communication layer, right? Your data is communicated from your actual asset to the virtual space via data acquisition. So you collect data from sensors and then you transmit this data to your digital layer, where essentially you have deployed your machine learning models. The output of digital layer is what? The output could be, as you have discussed in this particular slide, you could have diagnostics, you can have forecasting, and you can have visualization as well. So once you get output from a digital layer, there has to be some recommendation made to the physical asset, recommendation or feedback. If you do not make this feedback, then this entire digital twin is of no use. So as you can see in this particular slide, you collect data from turbine. And this data is simply, for example, if it is gearbox data, you collect gearbox data and you train a machine learning model. The objective of that machine learning model would be to, let's say, do prognostic level of inspection. So prognostic level is again a what if analysis when your gearbox is going to fail. So essentially we are conducting remaining useful life. What is the time left for the gearbox to fail? So you do an offline training, right? Based on the historical data of the gearbox, you create a machine learning or deep learning model, and then you test that particular machine learning or deep learning model from the actual data collected. So this is the actual data. So from data acquisition, you get real-time data. You do some data processing, maybe you will filter some data, you'll do normalization. Filtering is done again to get rid of your unwanted noise present in your data, right? Because your model is expecting a data which is filtered, because we have done the same filtering in our offline phase. So if you give unfiltered data, then model won't be able to do a proper predictive modeling. That would result in an incorrect, I would say, RUL estimation. So RUL stands for remaining useful life. So if you want a reliable RUL estimation, this is very important procedure. Filtering and normalization of data. Because when you're collecting multitude of data, every data will have different range. So each data has to be normalized so that you can train your machine learning model in a fair way. So that is again a very common, I would say, machine learning term that we use. Then you have your recommendation engine, where you give all types of recommendations. It is nothing but feedback that is given to your physical asset. And based on that feedback, you take certain decisions. So this is physics informed modeling. You can consider this modeling for the gearbox part, where you have your aerodynamic torque that is concerned with the incoming wind speed, and then there is generator torque that is associated with the generator. Interaction of both these torques is impacting your entire gearbox operation. So yes, there's a set of differential equations that governs the drivetrain, right? There is a speed involved there's a rotational speed that is involved. There is obviously a damping factor. There's how much inertia is present in your gearbox. So all these factors, they impact your entire gearbox operation. And we are using the data essentially from these differential equations. The data collected becomes the source of our data to the digital twin. Your twin has to get data from physical layer, and what type of data that you give to your digital layer is very important. So if you are giving a completely unrelated data, then your decisions will be very unreliable. So it has to be meaningful. So selection of data is again very critical procedure for operation of digital twin. So your updates from the virtual space in terms of forecasts, they help in decision making process. So decision making process is entirely reliant on how good your data is, and what we can use in our digital layer. As you can see here in digital layer, your predictive model, right? You can use different type of machine learning models. Nowadays people are using deep learning models because you want to extract meaningful features from your data. Machine learning models, the main disadvantage is that you have to give features explicitly, whereas for deep learning models your features are extracted automatically. So that's one advantage of going ahead with deep learning based models. So they are good for forecasts, they give you reliable forecast. And if you want to improve your forecasts, you need a large historical database. Essentially, for wind turbine, we call it SCADA data. You need a large historical SCADA data. Yes, so this is what a deep learning model looks like. So this is a model that we deploy in virtual space where all the computations are done. As you can see, this is a model of an autoencoder. It's a particular deep learning model that tries to reconstruct input. So this type of deep learning frameworks can be used. This is not a mandatory requirement. People also go ahead with machine learning frameworks as well. But deep learning is, yes, it is popular these days. So what are the common architectures for your virtual space? You can go ahead with artificial neural network, right? Convolutional neural network. See, virtual space is nothing but the place where you deploy your machine learning and deep learning models. So your data from physical space is being sent to virtual space. Then you can use LSTM, yes, long short-term memory networks. These are very popular networks when you are dealing with time series data. So this is a good choice of deep learning model when you are working with wind turbines. Then you have autoencoders, and then you have GANs, generative adversarial networks. Generative adversarial networks, these are a special class of deep learning models where you try to identify between real and fake data, right? And we are using a fake generator model, and we try to use a discriminator model, which distinguishes whether the data is real or fake. So to predict your cyber attacks on your wind turbine, we can use this topology. So cyber attack, cyber physical modeling is again very important aspect of wind turbine. So prediction of cyber attacks, we can go ahead with this generative adversarial networks. Now, what is good for your virtual space? You obviously, as we have discussed, large historical database will improve the performance of virtual space. You have to avoid overfitting. So avoid overfitting means that if your training data is too good and your testing data is completely opposite, then you would see a very poor performance from your virtual space. So it's a machine learning term. Overfitting is a machine learning term. So those who are familiar with machine learning would know that we always try to avoid overfitting in our machine learning algorithms. Then one can always test spatial dependence along with temporal one. So let's say if you're collecting data of gearbox, you can also collect data for generator because it is spatially close to your gearbox. So generator operation can affect gearbox operation. So if your model is data dependent, you can always go ahead with spatial data as well. Then deployable, scalable, and less burden on hardware. Yes, again, very important point that your model that you have created or your virtual space, right? It has to be deployable, something that you can deploy on site, something which can be scalable. What if tomorrow you are getting a very high frequency data? What if the volume of data increases? Is your algorithm smart enough or efficient enough to handle that large amount of data? So that volume of data, if it increases, you should be in a position to extract meaningful features from that increased volume of data. So that is one, I would say, requirement of your model as well. Then recommendations. So this is the final part of digital twin. Once your virtual space is ready, once your virtual space has started making some decisions, it has to make some recommendations. So that recommendations could be in form of alarms. You can have alarms in times of critical events, which can indicate failure, that yes, this failure is going to happen, or this is something wrong with your gearbox, or there is something wrong with the vibration of the bearing. Then you can have remaining useful life activity tracker. So you can track what is the remaining useful life. Now, this is directly the output of your virtual space. And these outputs, they have to be used. They have to be used in a qualitative way by the wind farm operator. Then the wind farm operator can take an appropriate decision. So the feedback that we have talked in previous slide, if you can see, this feedback is essentially nothing but the feedback to the user input. In this case, this feedback would be to the wind farm operator, right? The wind farm operator can track the RUL, and then if he sees that the RUL is very near about, then maybe some decisions can be taken for the gearbox. Maybe you can change the oil, maybe you can replace the bearings, and so on. Health index and critical thresholds, yes, again, very important aspect of recommendation engine. Your recommendation engine should tell you what is the current health index. So health index is just a number. So if a health index is close to 0, you would say that yes, your turbine is close to failure. If health index is close to 1, it would indicate that yes, turbine is currently healthy. So these thresholds, they differ from turbine to turbine. Every turbine would have a different threshold. Essentially, if the rating of turbine is different, right? If you are going with a multi-megawatt turbine, or if you are going with a small scale turbine, these thresholds will be different. And to identify these thresholds, you would need significant data. So yes, that is where the entire uh, recommendation engine works and helps, right? So thank you so much. That would be it from my side. Thank you so much for your patience. I hope I was able to uh, convey some meaningful information regarding the digital twins, and I hope many of you would get interested in similar allied areas. Maybe you can use digital twins for solar, for power electronics, control systems. So application wise, digital twin has a very large application base, and this would really be something that industry looks forward to for the next 5 to 10 years. That would be it from my side. Thank you so much.
Okay, so for questions, any question?
Does anyone have any questions? Okay, then now I'll hand over Harshita to say the vote of thanks. Harshita, over to you.
Good afternoon, all. On behalf of SRM University Power and Control Society and whole EEE department, I take this opportunity to propose vote of thanks to those who have contributed to this seminar on digital twin framework for wind turbine condition monitoring, organized by our institute. At the outset, I thank our honorable speaker, Dr. Arsh Diman, Assistant Professor, Department of AI and ML, for spending your crucial time delivering on the topic of the day with us. We are really enlightened with your knowledge and presence, sir. The session was very interesting and we came to know about some new things today. I would also thank our HOD, sir, Dr. Taushif Khan, Club Coordinator, Dr. Satyavir Singh, and all other faculties, HOD scholars, and students present here. Thank you so much, everyone.
So, sir, we will take one quick pick. Okay, so you can just
Sure.
You can minimize your screen, or you can
Yes, sir. Yeah.
okay. So I think okay. Thank you, sir.
Thanks a lot. Thank you so much.
For
Thank you
your-
again to Dr. Tausif and your team at SRM. I'm completely honored to deliver a talk on this topic, and hopefully it will ignite a lot of researchers, MTech and PhD students to pursue their research in this area. Again, if anyone wants to contact for any research collaboration, I'm available on LinkedIn, and we can connect on LinkedIn and have a great discussion there as well. Thanks a lot.
Okay, thank you, sir.
Thank you. Thank you.